again, year 13. Time to continue with rates. You can see the title up there on the whiteboard. It says rates, the 9 graphs and half-life. Really important. The half-life bit is one of the favourite types of questions, so it's really important we do that fully. But before we can do that, we need to be aware of the 9 graphs, because the half-life comes out of one of the 9 graphs. So we need to know about the 9 graphs. So there are 9 relatively straightforward graphs where either concentration, time or rate are plotted literally as a pair. So there were that pair, and the end 2 as pairs. And it's also related to 0, first and second order. So if you put all that together, you get 3 graphs for that pair, 3 graphs for that pair, 3 graphs for that pair. That's 9 graphs. But most of the time you see a graph and they ask you what is the order of reaction, because the graphs are about identifying the order of the reaction. It's going to be the first 6 that I do. So do make sure that you are making notes. If you need to pause me so that you can sketch the graphs, because they are only going to be sketch graphs on my whiteboard. There we are. You can, if you're familiar enough with the content of rate, pretty much deduce what the graphs will be like. Although that probably is a skill not for today. But once you've understood what's going on, you'll appreciate why the graphs are the shape they are, and it's the reverse of that process. So what I'm going to do is I'm going to put the 9 graphs on the board, and then I'm going to get you to sketch. I want you to pause the video and sketch them, and then I'm going to go through the appropriate things to say about each one. So I'll get the 9 graphs on the board and I'll see you in a moment. So here are the 9 graphs. I'm going to get you to pause me in just a moment, because you're going to need to sketch them down in order to do what we're going to do. But I just want to point out that, like I said, there were 3 graphs for 0, and similarly for first and second. And the difficulty is that they start to look the same. They start to do similar things, like this graph and this graph look the same. And what's the difference between that? And these two look the same, and so on. So what I need you to do, because you're going to need to write things about each graph, is that you're going to need to leave some space around each graph to write some things when I talk about them. So I've got them quite close together. I think you need them further apart. Maybe not arranged like I've got them here would be more sensible. Like those, we're going to do this way, then this way, then this way. But you might like to have them underneath each other, and then move on to these ones underneath each other. But I'm going to ask you to pause the video, and so that you can get them ready. So if you pause me now. Okay, so you've now got your 9 graphs. We'll talk about these 3 first. Concentration versus time. Now what these show, this is a slight curve, and if you've got it as a straight line you weren't looking carefully enough, but it is a slight curve. It's not a very deep curve. You may need to redraw that if you've not picked that up. Now, concentration versus time. The concentration of any reactant decreases through the period of time that a reaction takes place, because it has to get consumed. It is about the way that it is consumed. Now, the speed it is consumed is the gradient of the line, the tangent of the line for these two, because they're curves. This one here is a straight line, constant gradient, constant speed. So that's what you need to write down. Constant, it's a fixed gradient and a constant speed. Remember, you can just pause me to catch up and restart me. This one is a slight curve, so the gradient is changing, it is becoming less as time goes on, as the reaction slows down. This is similar. It is becoming less as a gradient, meaning it is slowing down over time, but it is a more dramatic slowing down. And the difficulty comes in when you plot these, you can't visually look at it and go, oh, that's a first order or that's a second order. So if you plot concentration against time and it's a straight line, you know it's zero order. This is the point of the graphs, is that the graph, by looking at it and maybe analysing it, and I'll tell you about that in just a moment, you can determine whether it's zero order, first order or second order. It is usually to determine the order with respect to a particular chemical, because otherwise you're not getting the information. But it can also be the overall. You'll never get this one for an overall order because every reaction has something in the rate equation. So this can't be an overall graph. Neither can these two for that matter. They can only be for individual components. But these ones can be for overall or individual depending on the setup, and we'll talk about that very soon. Now, these two, difficult to spot the difference between them, but that's where this half-life comes in. Because when you analyse these two for half-life, and I'll go through how you do that, and there is an attached sets of data about this as well, which you need when you get to practice this. The way you analyse for half-life tells you whether it's first or second. So that's why this graph line is important, because of the type of question. It's a common question, is you get a set of data, you plot it, and you determine the half-life in order to determine whether you're looking at first or second order. I'm going to use the word kinetics, first or second order kinetics. Kinetics means analysis of rate of reaction. Okay, that's the first row. Second row, rate versus concentration. So here, you're looking at what's going on in the rate equation, because time isn't in the rate equation, but the rate equation is rate equals constant times the concentration with their orders as powers. So if you've got a zero order component in the rate equation, zero order doesn't affect the rate. Concentration to the power of zero becomes the number one, and the number one doesn't change, it just stays as one, doesn't do anything. So therefore the rate is unaffected by the concentration of the chemical to which it is referring. And remember, it's a zero order one, so it can only be with respect to. So the rate is unchanged, hence it's a straight line across. It ploughs on at the same speed and doesn't change. When you look at first order, rate is going to be proportional to the concentration. So R equals K. K is the constant of proportionality. Concentration to the power of 1. Concentration. And therefore it's directly proportional. Directly proportional relationships are straight lines. And because it's R equals K concentration, there's no add-on bit at the end. You know the Y equals mx plus c thing in maths? There's no shifting of it up and down with the plus c part at the end. So it comes straight out the origin. So that plus c part lifts it away from the origin in one direction or the other, depending on what it is. Now when you come to this graph, the rate is proportional to the concentration squared. So y equals x squared is a curve. In fact, it's in maths, it comes back up the other side as well. But we can't have negative concentrations, it's a nonsense. So we start there at zero. That should actually start at the origin. I've drawn it a little bit badly. And it whips up, and it curves up. So that the rate, as the concentration increases, gets increasingly faster. It's a squared relationship. I'm going to pause so that you know that if you want to stop me there. Now we'll go on to the third row. These are ones that you don't see quite so often. Rate versus time. So how does the rate change through the progress of the reaction taking place? So in zero order reactions, the rate is unaffected by anything going on. So the rate just carries on the same for a zero order, just ploughs on at the same speed. Heads it straight across, which is why those two graphs look the same, because the rate is not being affected by the chemical. Here, because this is a straight line, this is a reversed straight line where the rate just gets slower and slower with a descending straight line. So it's related to that. Here, the rate rapidly slows down and then it tails off slowing down and gets sort of quite similar in rate. And those are the graphs. If you want to, at this point, think, oh, that was all quite a lot, you can rewind me and run through it again. I really think it's important that you have your notes next to each one of the graphs. Maybe you should replay the video to make sure you haven't missed any of the important things for each graph. We're not quite ready for the half-life bit, which applies to these two graphs, because there's something I need to tell you about the setup that you do in order to get these. But I need to get these off the board in order to do that, and I'll see you in a moment. Okay, this bit here is about the setup to collect the information to plot those graphs that you've just had. Equimolar versus, I've not called it excess, I've called it gross excess. Now gross excess is a horrible word, gross excess. But it means very much different concentration. So when you have equimolar, now it doesn't have to be equal to follow what goes on with equimolar as a consequence. So that's why I've put equal or near equal. What does near equal mean? Not dramatically different. So here's some examples of things that would fall into the category of the equimolar discussion. Obviously that one, because they're the same. These are not dramatically different, 0.5 and 0.75. These are concentrations, by the way. And even that, even though this one's twice that one, they would still fall into equimolar. Now why? Well, it's about whether the concentration of, this represents two different chemicals each time, whether the concentration of both of those chemicals will noticeably decline as the reaction takes place. So this one, presumably both will go down fairly similarly and keep not dissimilar in concentration. It does depend on the rate equation, that discussion. Here, this one's a little bit bigger, but it will, if they're reacting in a 1-to-1 ratio, if this one goes down to 0.25, it will still make that one go down to 0.5, which is a dramatic difference compared to 0.75. It's, you've dropped it by whatever fraction that is, a third, which is a significant change. So it's whether both chemicals change significantly in concentration as the reaction takes place. If that's the case, you can't tell what each individual component is doing, and therefore what is responsible for the graph that you see, whichever one you're plotting. So it gives you what is called the overall rate information. So that tells you that only the sum of the orders that you would have in the rate equation. So even this one here, 1 and 2, if the 1 goes down to 0.5, that goes down to 1.5, probably. That's still a dramatic difference from 2. It's changed by a significant proportion. So when both of them noticeably change, it only gives you overall rate information. I've called it equimolar. It's kind of not equimolar, but it's not dissimilar in size. Now it's quite a long word, so I use equimolar. And a lot of questions say an equimolar mixture of, but whatever the chemicals are. gross excess, looking at probably something like 10 times the concentration of one to the other. So here, there's an example of a 10 times difference. If that goes down to 0.05, that goes down to 9.95, and it hasn't dramatically changed. And that's the key difference between these two. So this one has halved, this one has come down by a small amount. So therefore, this one allows you to access individual chemical information. So in order to determine the rate equation, this one doesn't allow you to determine the rate equation properly, only the overall. This one allows you to pick up individual chemicals. So there, similar example, 0.5 halved, that will come down to 4.75. That's not a dramatic change on the 5, percentage-wise. And if it was more than 10 times, it's even more clear cut. So this method, where you have not very much of one chemical in terms of concentration and a lot of the another one that is involved, allows you to pick up the one with the smallest concentration's contribution to the rate equation. And then you flip the setup and do the other chemical at low concentration and the one you were looking at the first time at the high concentration, and it allows you to pick up what the other chemical is doing, and then you can identify the structure of the rate equation. That never does. That does. And the mistake people make in questions is they miss the equimolar part. Don't miss the equimolar part. Because it will be pretty much one of the first words in the question is an equimolar mixture or something like that. And if you miss that and you go and do this, you're not going to get the answer right, because you're going to be talking about individual chemicals and you need to know it's that. So look for the setup of a practical thing. So this is a paper 3 type thing. This is a paper 3 setup, graphical plot analysis that you will need to be switched on to those two things. Now we're going to go on to the Halflife bit, which is the remaining part of the video, but I need to talk about what you need to do and get ready for it. See you in a moment. Half-life plots, really important. Now it is related, oh, I haven't put anything on the axes, it is related to those two graphs that I mentioned out of the 9 when you can't tell the difference between the curve. So it is, which one of those, I mean yeah, intentionally that is the first order, that is the second order, but it's quite hard to judge how deep a dip in the curve to do to get a first order one. I often sketch them and I realise when you analyse the numbers, the curves are not as indented as you think. So it's about how do you tell the difference. Now, Halflife should be ringing the bell of GCSE physics radioactivity, because radioactive decay follows the same kinetics. It doesn't have kinetics, it's not the way physics talks about it, but it follows the same graph pattern as first order reactions. So when something is first order, it will have a half-life behaviour the same as a radioactive decay. So that should be ringing a bell. It is similar, well not similar, it's identical in the way you do it. In chemistry we talk about consecutive half-lives, which apparently doesn't have a Q in it, if you can see the smudge, because I always spell it wrong. Consecutive half-lives. So that means you do a half-life and the next half-life comes straight on the end of the finish of the first one, and then the third one comes off the finish of the second one, so they don't overlap. There's no gaps, they're just not attached to each other, up against each other. Now the key thing here, this is how you tell the difference between this one and this one, if I've got those the right shape. First order, the half-life will be constant. Now, in the real world of plotting a graph with you you're in you've got a piece of graph paper, you're doing it by hand, it might not come out exactly the same. That's almost unrealistic. But what will happen is that it might be the first one, the second one is a little bit long, only a little bit longer, not obviously longer, the third one a little bit shorter, and so they all sort of stay around the same value, because in terms of plotting an actual graph, that's the sort of thing that happens. But the half-lives will not do this one, which is quite obviously the first one. The second one is noticeably longer, not just a little bit longer, but significantly longer, and the third one is even longer still. So that's how you tell the difference. Ones staying the same are going to be first order, ones that just noticeably get longer and longer and longer are going to be second order. What I need you to do now is, attached to this video is some data sets. There are 3, I think, without going back and having a look, because I don't have the sheet in the room here. I just want to talk about the first one. I need you to go and plot that graph, and I need you then to come back with the graph in front of you so that I can make sure you know how to analyse for Halflife. The data set is for a chemical you won't necessarily know about, depends on which order you've done the chemistry course. It matters not what the chemical is, it's just it is a real example. It's a chemical called benzene diazonium chloride. Benzene diazonium chloride, and it may not be in your course, not all A-level courses have benzene diazonium chloride in them, but if you do dyes, it's the way you go and make dyes, and you have to make a dye, keep it below 10 Celsius, or you lose the intermediate that you make in the process. That intermediate is a benzene diazonium compound of some form. And if you let the temperature go up, it breaks down and gives off nitrogen gas. So it will go down in concentration. Classic rate setup. When you look at the data says, now when you look at the data set, it says 10 to the 3 times the concentration. You might be a little confused by that, but what it means is the concentration has been pre-multiplied by 1000. So the actual concentration, that first one, 5.8, which is not 5.8 as the concentration, it's 5.8, what's 5.80, I know, 5.80 times 10 to the minus 3. And then it's pre-multiplied by 1000, just so you don't have to have down there all the standard form down the edge of the graph. You can just go, oh, let's do the 5.8. But you do need to put it's 10 to the 3 times the concentration when you label the axis. It's just a way to make the numbers easier to put on a graph. Now you will need to plot by hand the data set 1. So you're going to have to get a sheet of graph paper. So I have attached to in the see more part, if you open up the information about the video, apart from the data set sheet, there's also a sheet of A4 graph paper for you to print out. And you will need to, if you haven't got any graph paper, print that out. Yeah, you're going to need to do some printing. So we're going to have to pause the video for quite a while whilst you print out the graph paper if you haven't done it, print out the data information, the data sets, and plot the graph. We're going to analyse together data set 1. There were 2 other data sets for you to practice on, and there'll be the answers for those as well. But you need to plot what we've got of the data set 1, concentration up the side, time along the bottom, and it will look like it will be a curve, but the question is which one of those curves is it? Well, so you're going to need to pause me, do all of that, and I'll see you after you've done all of that, because there is no point in going any further in this video unless you've plotted the graph and you're ready to do what we're about to do. I will see you after a particularly long pause for you, but not for me. So you've plotted your graph. I've managed to, in that time, find a rather larger kitten than last time you saw them. That's especially for the person who asked. Okay, so you should have a graph. They may make a reappearance, the two cats are running around. So you should have a best fit curve. It should be quite a close fit because I constructed the data rather than use some from an actual experiment. Now, how do you do consecutive half-lives? You may have had a go already and you may know what to do, in which case you're all good. 5.8 is the first point on the graph. 5.8, so you go, I'm going to halve the concentration. Half of 5.8, 2.9. So there's 2.9. And what you're going to do, I'll get my special non-ruler ruler out. It's a little bit wobbly, but it's quite hard drawing on a whiteboard. So you're going to do a line across to when it hits the line, the best fit line, and drop it directly down. People sometimes have difficulty dropping a line directly down or getting it across. You just need to make sure your ruler is parallel to the printed grid. And then you do. Then you should be okay. So what you're looking at is... Oh, did you hear that? That's the other cat making a play for going outside. So the time difference, therefore, between there and there is the half-life. Okay? And you can hear the cats careening around in my house. They were out earlier. They've come in since we did the first bit. So you get a time in seconds for this first halving of the concentration. You then do it again, and you can see I've pre-prepared where I'm going to go. Half of 2.9 is 1.45. So and you drop that down. Your graph will be better than this. This is just a hand-guessed curve. Yours is a plotted curve off the points that we have. And so what you do now is find the length of time for it to halve again. So you start at that time. If I call that T1 and I call that T2, and that is T1 minus T0, that's T0 there. So there and there. Now then you do it again at 0.72. That's a bit far for my shoddy little orange ruler, but you do that and you drop that down there. Now, when you do that, you will get 3 what are called consecutive half-lives, because the next one begins where the previous one finished, and that makes them consecutive. And if you do that on the graph, I'll tell you what I think it should be in just a moment. So I need you to pause the video and go away and do your half-life analysis of the graph that you've now plotted, and I will see you shortly for the big reveal. Different sort of reveal. Here's the other somewhat larger kitten. This is the noisy one. Hello. Anyway, that's again for the people who wanted to know. So, you do that. Yours, well, quite frankly, the data is set up so that these should come out the same. It should be close to 460. Were you? Well, if you do the mean value of the 3, see, you won't be... Oh, and there it runs off of the brown cat. The average should be pretty close, the mean value, to 460. It doesn't have to be dead on 460. When you get this kind of question in an exam, they have a range of acceptable numerical answers, and if you fall within it, you'll get all the marks that are allocated for that. So this analysis technique allows you to determine by looking at the value of consecutive half-lives, the following. Your plot of this should have come out equal half-lives, give or take a little bit because it's a graph. That makes it first order reaction kinetics. The benzene diazonium chloride, the compound with the organic formula, power of 1, because it's equal half-lives. The alternative is that the half-lives noticeably lengthen. So we're not talking about a couple of seconds or 5 seconds or 10 seconds even. But the first one, if it were 460, the next one would be somewhere around about the 550, 600 mark, and so it would lengthen noticeably each time. The reason my graph looks a bit not like yours in terms of these is that my curve is too digged in. This is why it's quite difficult to see that you've even got a curve for first order reaction kinetics. But rest assured, when you do an exam question, the data will be very close to perfect. So this graph that you have plotted, data set 1, first order reaction kinetics. There are 2 other data sets for you to do half-life practice plots with, and well, the answers are there once you've done it, just to see if you came close to what I thought. Important exam technique, because you get this kind of question quite often. There we are. Allows you to differentiate between first and second order reaction kinetics when you've got concentration and time. Of course, it won't be the way you analyse concentration and rate. That's just one of the 9 graphs that you look at, and that's where those come in. Thank you for watching, and I'll see you soon for more rate of reaction. Bye.